Suppose there are two rockets attached by a very long, thin string. If both rockets suddenly accelerate the same amount at the same time, they should stay the same distance apart. Except now they're moving, and in our universe, moving objects undergo length contraction and get shorter in the direction of motion. The rockets and string should each have their lengths contracted and be shorter. So do the rockets and string as a whole contract, with the two rockets closer to each other? Or do the rockets individually contract but stay separated the same amount, while the string shortens and risks snapping? Assuming the string has no significant strength, the spacecraft shouldn't move any differently than if there were no string at all, and since they both underwent the same acceleration, they should stay separated the same as when they started, which means when the string shortens, it must snap. But how? Is length contraction a real physical force? Yes it is, from a certain point of view. The electromagnetic forces which hold the string together undergo length contractions too, and so the very atoms and intermolecular separations within the string are contracted, literally pulling the string shorter, or tearing it apart if its ends are tied to, I don't know, too heavy spacecraft. So length contraction makes the string tear itself apart. But from another point of view, the string breaks for a different reason. Because from the perspective of a moving object, events that used to be simultaneous no longer are. In this case, from a perspective moving along with the spacecraft's final speeds, the front spacecraft actually accelerates first, and so for a while is moving away from the back spacecraft. By the time the back one catches up, the rockets are farther apart than when they started. All this is much more easy to keep track of if you use spacetime diagrams to correctly describe the whole situation, rather than just trying to think about length contraction on its own, or relative simultaneity on its own, or whatever. But the point is, from a moving perspective, it's the rockets that snap the string. Okay, so if the string snaps, then why don't all objects explode when they move? Why don't the spacecraft tear themselves apart when they accelerate? Well, an object tearing itself apart can only happen if different pieces of the object independently accelerate, like how the two rockets each have their own propulsion. Normal objects aren't like that. Instead, one part is pushed or pulled, and then the intermolecular forces in the object transmit that acceleration to the other bits of the object. And when those intermolecular forces, which are electromagnetic, experience length contraction, the object as a whole simply contracts. But anytime there are multiple sources of acceleration on multiple parts of an object, in principle, it could get torn apart by length contraction. Or you might say it gets torn apart because those different parts start accelerating at different times. It depends on your point of view. Literally. In our universe, it's not just space and time that are relative. In some cases, it's also whether you're torn apart or whether you tear yourself apart. In putting together this video, it was really helpful for me to work out the space-time diagram for Bell's spaceship paradox myself. And that's exactly the idea behind Brilliant, this video's sponsor. Brilliant is based off the principle that active problem solving is the fastest path towards mastery of a new concept or skill. And now they've taken it to the next level with tons of visual interactivity across their math and science courses. You can interact with gears and pulleys and computer programming and the Pythagorean theorem. To gain a deeper understanding of science and mathematics, and to sign up for free, go to brilliant.org/minutephysics. The first 200 people will get 20% off an annual premium subscription with full access to all of Brilliant's courses and puzzles. Again, that's brilliant.org/minutephysics. And thanks to Brilliant for their support.